In this demonstration, we will be showing a reference implementation of an automated meter management solution deployed by the Energy and Utility Solutions Lab in Austin, Texas. First, let's describe the interface. The left side of the screen shows the Automated Meter Management Web Interface. The AMM web page shows a map identifying the location of the utility's electric meters. The top right pane shows power consumption of the electric grid. The lower right pane provides meter access where meter readings are displayed and interaction with meters take place. On the upper right-hand frame, a brief description of the solution is shown, and the lower right-hand frame shows a live video feed of the Austin Lab displaying a smart electric meter, a Prolifix thermostat, and a utility lamp. Imagine a hot afternoon in August, when every air conditioning unit is running and the utility is stretched close to capacity. The utility needs to shed energy load from the grid before things are stretched too far. Through the IBM AMM solution, the utilities are able to use a simple web interface to control end-user devices which are consuming power and turn them off. We envision consumers signing up with their local utilities for the automated metering option and getting a lower electrical rate as a result. The consumers would register certain devices in their homes as controllable, so that if there were any critical items, such as medical devices like respirators, heart monitors, or pacemakers, they would be excluded from control. Then, if the utility found itself in a demand outstripping supply situation, or if during severe weather there was damage to the system, the utility could shut down certain devices until the system was brought back into balance. This allows the utility to incrementally, and more importantly, temporarily, shut down certain devices to bring consumption back in line with supply. This is what we refer to as the intelligent grid, the energy system of the future, using a standard called AMI, the Automated Meter Infrastructure. We utilize the Web AMI interface, which means that it is implemented with a standard web front end to leverage the capabilities of Web 2.0 technology. If we look at the peak in the graph in the top right pane, it illustrates a spike in power consumption. The Utility Operational Manager will respond to this observed spike in consumption by performing load-shedding activities to avoid overconsumption that could possibly lead to a brownout condition. The Utility Operational Manager selects one of the meters in the left pane, which corresponds to our MUNET or Itron meters. As you can see, the MUNET meter has been selected. Selecting the meter shows the devices which are associated with it. Here we see that a Prolifix thermostat is powered by the MUNET meter. In the case of the MUNET meter, we use Internet Protocol, or IP, to communicate with the meter which has an embedded Linux operating system and an Apache web server. The Itron meter has equivalent functionality enabled through a proprietary interface and network. When selecting the Prolifix device, we are presented with a list of the services which are available or the operations that we can perform on the device. Here we use the drop-down list to select Conserve Power and click on the Enforce Action button. As you can see, by selecting the MUNET meter on top, we have just powered off the light in the Network Operations Center. Selecting the Itron meter and executing Conserve Power powers off the landscape lighting on the opposite side of the lab. Using the IBM AMM solution, the utility can control remote electrical devices in a residence or business. The solution enables this control through a standard web interface. In this case, we are turning off a lamp, but this could be any electrical device such as an air conditioning unit or some other high energy consumption device. When we execute the Conserve Power command, we are communicating with the Prolifix thermostat to turn off the light. In a real implementation, the thermostat would control the air conditioning system. When the high demand situation passes, the operational manager can return the devices to a normal operational state. Using the Solutions Architecture for Energy Framework, or SAFE, we can communicate to the meters through a Common Information Model, or CIM, which converts our generic request into device-specific syntax. It provides a mediation layer so that we can use a standard message payload. On the device side, we go through the Service-Oriented Device Architecture, or SODA, to talk with the IP thermostat. We use web services to interact with the SOTA server, which translates our request to send the conserve power command. The translation on the consumer side is similar to the function that CIM provides on the provider side. Next, we'll go through a meter read scenario. On the map, let's select one of the two meters to bring up the meter list, or by selecting the endpoints table. By selecting one of the listed meters, we can then go to the lower right pane labeled Meter Access and select the Demand Meter Reading radio button. Clicking the Get Readings button allows us to get a remote meter read in real time. This demonstration uses IBM WebSphere Application Server, which provides the middleware layer, IBM Process Server, and WebSphere Modeler. These components are used to model and execute business processes and integrate legacy applications. DB2 provides the backend database, and WebSphere Smash provides a Web 2.0 graphic user interface. Let's now examine a remote connect and disconnect scenario. We'll switch our camera view to show our house location, as shown on the right, where consumption is being measured by an Itron meter. The meter is currently active and the landscape lights are on. Austin, Texas is a college town and home to the University of Texas, which is the largest university in the nation. In any given semester, there are tens of thousands of students leaving or moving in. It is estimated that Austin Energy has saved $60 million with the intelligent utility network and the automated meter management solution through the labor saved by providing remote connect and disconnect capabilities. Remote connects and disconnects are some of the features provided by the Web AMM solution that leverages Web 2.0 technology, open industry, and technology standards, enabling these functions to be performed from a central office. So let's now select the Endpoints table in the left pane under Consumer Endpoints, then select a meter. Now click on the second tab labeled Meter Control in the lower right pane. From the drop-down list, we select Off, then click Set Control. This will power off the selected meter. We can also power on the meter or arm it. Arming the meter places it in a ready state so that power is enabled as soon as the consumer resets the meter. The consumer is informed that the power is available and that they should turn off all electrical devices and appliances, then reset the meter to turn the power on. Now let's take a look at the map on the left. We'll reload the Web AMM page to display the map with the meter's location and status. As you can see, the Itron meter's location shows in red, indicating that it has been powered off. In summary, Automated Meter Management Solutions provides utility companies with new and improved capabilities to better manage access to their device infrastructure and allows for demand management. Energy customers from around the world, such as Austin Energy and Centerpoint Energy in the United States, Dong Energy in Denmark, and Oxio Metering in the Netherlands, have already deployed IBM AMM solutions. With features such as remote reads, remote connects and disconnects, and remote device management, IBM is enabling utility companies to be better prepared to face the challenges of a new era. We are making the utilities smarter with IBM Smart Grid Solutions.